to start off, me and some of the other maintainers are going to be talking through basically what's new in Valkey 9. Valkey 9 isn't quite launched yet. It'll be launching later in September. But we're hoping to give a sneak peek of the stuff we're working on and also give a little bit more context about why we built it, how we built it, to hopefully, tickle the inner engineer in a lot of you folks. So my name is Madelyn. I am one of the maintainers of the Valkey project. I'm also going to be joined later by Ping and Ran, who are two other maintainers. We have two other maintainers in the room, so if they could raise their hands so you know who they are. Yeah, we have Victor Soderquist and Harkishan Patro. Also two great people if you're really curious about the deep technical, how Valkey works inside. We also have some other maintainers in other projects, so if the folks from Glide would also maybe raise their hands, or other projects in the Valkey community who are maintainers. Kyle also, thank you. The folks from libvalkey and the Python client. Also, so there's a lot of people in this community in this room who are part of the community. So I'm very excited to talk through all that. So before we get too far into this, who here knows basically nothing about Valkey other than maybe it's a key value database? Perfect. So I do need to do this slide. So, Ricardo, did I miss Ricardo? I did. I'm so sorry. You didn't raise your hand, and so I didn't see you. I'm so sorry. We also have Ricardo, another great maintainer of the project. Dimitri, you didn't raise your hand either. There's so many people in this room. But I digress. We're getting back on topic. So Valkey is a key value database. It is compatible with Redis open source 7.2. We were created as a hard fork of the project about 16 months ago. We are trying to continue on in the open source permissive license that Redis had before the fork, which is a BSD 3-clause license. It's a very permissive license. You can use it for basically whatever you want. And we strive to be very community driven. We just talked about a lot of maintainers. I'm from AWS. We have folks from Percona, folks from Google, folks from Oracle, folks from Ivan, folks from Ericsson. Hopefully I didn't miss a company. So, so we strive very hard to have a very big inclusive community. So if anyone here is interested in helping contribute, or they have a feature request, we would love to help you on board and become contributors to the project. So one of the things that I think is very exciting is Valkey was a hard fork of Redis open source 7.2. And so at that point in time, we didn't have much net new functionality. We were just a fork. We're a permissively licensed fork. But a year ago, at this very conference, Open Source Summit EU, we actually launched the very first version of Valkey, which was Valkey 8. And so I think it's nice to kind of go and do a year in retrospective, what we've built in the last year within the Valkey project. And I'll call out a couple people in this room who built some functionality. So as I said, Valkey is a key value database. So one of the first things we built that was contributed from AWS was we improved the multi-thread performance to get our famed 1 million requests per second, which is a quite high throughput. We also, Valkey can scale both by adding threads, but it can also scale by adding replicas. So you can basically copy pieces of the data to another node and then also serve requests from there. We call this replication. You can serve the data from replicas. So we also built a feature which we call dual channel replication, which basically almost doubles the speed of replication. We also had, from Google, they built an enhanced slot migration reliability improvement. So slot migration is an alternative scaling mechanism of Valkey where you can add more shards of the data. So instead of having just one complete copy, you have multiple different nodes with different parts of the data set, which we call shards. And that had a lot of failure modes in the open source community, and Google was very excited to help make that much more reliable. And Ping will later talk about how we made it even more reliable with the new functionality in 9.1. So this was our big release in 8.0. You can see it covers a lot of stuff like performance, reliability. So that was launched last fall in September. Earlier this spring, we launched Valkey 8.1, which had some different types of improvements. So Ericsson produced an improved core data structure for the Valkey engine, which reduced memory overhead by up to 20%. if there's a very good talk on it, if you're curious, that we presented earlier in the year about this. We also started to look into other types of new functionality. Redis was well known to be a very easy to use, and we're trying to kind of continue on in that ethos. And so we tried to make it easier to build some more advanced applications. We had vector similarity search, Bloom filters, which are a probabilistic data structure. And we also had native JSON support, which is the ubiquitous data transfer format in most cloud applications. And then we also worked on building more introspection, more observability. And so that was the other big part of Valkey 8.1. So that all got launched earlier this year. One of the reasons I like to bring all this up is I was at the recent open source summit in Denver, and someone came up to us and they're like, yeah, we heard about Valkey, but we haven't been following anything you guys have been doing. So I also think it's always good to just sort of rehash kind of what we've been working on, why we've been building it. And so now that brings us to today. So we have a Valkey 9.0 release candidate, which means that the code is out. You can go download it. We have a container you can go pull and try it out. All the functionality we're going to be talking about today is in that release candidate, but it's not finalized yet. So if you try it and you find a bug, or you were like, wow, it'd be really nice if I had X, Y, or Z, like now is the best time to provide that feedback so we can go and improve it. So there's a lot of functionality in the release candidate, but we're going to be talking about 3 specific things today. So we're going to be talking about multiple databases in cluster mode. So we talked about cluster mode as the horizontal distribution. I'll talk a little bit about what a database is. Atomic slot migration, which is this reliability improvement that is an extension to that reliability improvement I talked about. And then also adding expiration on what we call hash field. So we'll get into more specifics about what all that is. But that's kind of like the main agenda of what we're going to be covering. So I'm going to start off by explaining that first feature, the multi-databases in cluster mode. So I'm going to start by kind of giving an overview. Who here knows what Mastodon is? Great. So for those that don't, Mastodon is sort of a Twitter clone that's more distributed. And Mastodon actually can use Valkey as a cache for timeline generation. So the way that works is, this is a little simplified of a version, but basically when a user kind of connects to the Mastodon server and their timeline isn't generated, they will go and check first to see if it's in the cache. So the cache can be in Valkey. And if the data is not there, Mastodon will go and generate that timeline for that user and then push it into the Valkey cache with the time to live. So if the user kind of doesn't log in for a while, Valkey will automatically kind of kick that data out. So one thing we kind of started to see with a lot of our users is they wanted some form of like namespacing, so that if you had basically 2 different servers and you want to connect to just one Valkey instance, since it's often easier to just run one versus a bunch of different distributions, they wanted to basically point the same Mastodon end servers to a single database. And that might work if sort of all of the keys happen to not hash to this, basically didn't have the different servers didn't have the same information, but sometimes there would be conflicts. So one way that, I don't know why there's a duplicate side. Oops. Oh no. What is it doing? So one way users solved this was that they would basically prefix. So Mastodon has support to basically say to prefix the specific keys. So you can say server 1 prefixes all of their information with server 1, and server 2 would prefix everything with server 2. And that worked okay. You have a nice flat key space. It works well with the access control system in Valkey. But one of the downsides is you have larger keys. If you say want to just completely delete all of the keys from one of the servers, you have to go scan through everything. It's a little bit cumbersome. So one of the built-in functionalities in Valkey is what we call databases. So these are kind of like logical namespaces. So you can basically split off server 1 into database 0 and server 2 into database 1. And so this gives you a bunch of functionality. You can do stuff like get info key space, which surprisingly doesn't tell you about this conference. And you can also do things like FlushDB, which will delete all of the data within a specific database. So that's an introduction of what databases are. And up until Valkey 9, databases were not supported in cluster mode or horizontal distribution. So if you had very large installations of servers, you wouldn't be able to use this configuration. So to give a very brief sort of overview of what cluster mode is, so as I said, it allows you to horizontally distribute your data, so you can have multiple shards of your data, and they're broken down to what are called slots. Ping will get into more detail about what exactly a slot is in a second. But suffice it to say, what you need to know is that the way we implemented this is instead of saying, some set of databases are on some set of nodes, some databases are on others, it was basically most straightforward to basically just have each database also have these concepts of slots. So when you were basically, if you would like to add a new shard to the cluster, you'll basically add these new databases to the new nodes and transfer all the keys in those slots over. So now in Valkey 9, what you're able to do is basically continue to use your application as it was before. You don't need to do any prefixing, and you're able to basically simplify your application and just connect to DB0 or DB1 for each specific server. So I know I kind of explained this at kind of a high level, but I think it's kind of important to see kind of where we're thinking, what we're building on top of. So if you're interested, the summary is cluster databases provide logical namespaces that can scale horizontally, which we weren't able to do before. Some technical implementation that's good to know is they have zero overhead if they're not being used. So effectively, the way cluster mode was modeled before is there was only one database, DB0, and as long as you continue to use that, you'll see no extra performance penalty. And we're also trying to make databases more of a first-class citizen moving forward. We're looking to add better observability, monitoring, and access control around these logical databases. So this is the first feature that I think was interesting and good to know. And I'm going to hand it off to Ping to talk about that second feature we talked about, which is atomic slot migration. So Ping, welcome.
All right, can you guys hear me? Okay, thanks, Madelyn. My name is Ping. I'm also one of the Valkey maintainers. Today I'll be walking you guys through this new improvements, major improvements in Valkey 9.0. So everybody knows that horizontal scaling is a very important key requirement or property of any distributed data storage. So in the past, we have the so-called now legacy slot migration, which is the process that Valkey has been using to scale up a cluster horizontally in the past. Now, there are multiple issues that we have fixed in the previous version, like Madelyn just mentioned, but then still some fundamental problems remain, which can potentially lead to degraded performance, broken application logic, and also obviously the major operation headaches. Probably you guys have, maybe some of you have already experienced in the past. So with that, so I'm gonna take you guys through the problems that with the existing so-called the legacy slot migration process, and then talk about the solution that we introduced in Valkey 9.0. So first of all, before diving into the details, I would like to quickly cover the slots, as Madelyn has promised a few minutes ago, that slots is a very important and key concept in the Valkey cluster. Valkey cluster is a key value store. It has this key space that needs to be partitioned in order to scale out. So slots is this concept of buckets that Valkey uses to partition out its key space. And for every key, there is a deterministic slot number that can be assigned to the key. And this is actually determined in a very simple way, that essentially taking the key name through the CRC 16 and the modular by the number of fixed slots in any given cluster. Note that the 16,384 is the fixed number for any given Valkey cluster, regardless the number of shards present in the cluster. So what's shown here at the bottom of the slide, it's a very simple cluster with 3 primary nodes, each owning 1/3 of the slot ranges. And obviously, the slot range does not need to be contiguous. So there could be all different kinds of distribution. Here is the most simplistic view that we can see here. So this is the basic. With the basic of the Valkey slots, we can look into the potential issues that we have been experiencing today with the older versions of the Valkey cluster. I think the core issue here really is because the existing slot migration process exposed the internal states to the outside world, the application. So for instance, so what's shown here is a slot 1, 2, 3 that has 2 keys in it, and then it's about to be migrated to a different node in order to scale out the cluster. As we can see here, today, when migrating a slot, we move the keys in the slot one by one. The action here is really move and then delete the key from the original node. Now, after this migration is done, but before the entire slot is migrated to the different node, to the target node, the source node still owns the official slot, which means that any client trying to access the key that has been migrated will get an error back ask, and then this requires the client to retry the target node. This obviously will add another network hop here, increasing the network latency and an additional processing overhead, which is suboptimal. On top of this, if this happens to a multi-key operations, now we will see a even worse problem here. As illustrated in this example, you can see that the key also, it's essentially the same example, but then this time the client's trying to access 2 keys rather than 1. Now this request, unfortunately, will be rejected by the source node because source node only has partial results. It cannot fulfill the request, but it cannot also redirect the request to the target node because target node also doesn't have the full view. As a result, a try again error is returned. I would call this a mini outage in that sense because the client is unable to get its data even though the data is still present in the cluster. Now this situation will last until the entire slot is migrated to the target node. During that period of time, any multi-key operation in this category will be rejected. So those two cover the potential impacts on the client side. Now, as far as the operator or administrator is concerned, there is an even bigger issue. That's essentially the large key handling case that I'm trying to demonstrate. In this case, we also have like this partial migration that keys are moved one by one to the target node. Now, in the first case, first key case here, A is pretty small, so obviously it can be migrated successfully without any issue. When it comes to the second key, because this key, right, well, we have seen a lot of users are using very large collections that have a lot of keys or members fields in that. So in order to migrate this kind of keys, a significant amount of memory will need to be allocated on the target side, sometimes exceeding the capability of the target, the capacity of the target input buffer, which will result this migration of the key getting rejected. When this happens, basically the entire slot migration will be paused. There is no other ways but to choose one of the two options in order to unblock this. So the operator has to face, this very tough decision. Either you need to delete the large key in order to unblock it, or you have to force slot migration by assigning the slot blindly, forcefully to the target node. In either case, you end up losing data, so which is really not the ideal situation. With that, I'm going to take you guys through that the major improvements that we have added to Valkey 9.0. So at a very high level, atomic slot migration can be considered conceptually a full sync replication at the slot level. So similarly, as any part of, not sure if you guys are familiar with full sync replication. But then as the very first step, any full sync replication starts with a fork of the parent process, such that we can take a snapshot of the existing data on this particular node. There's no difference here in this particular case. A child process is forked to create a snapshot. And then the snapshot will be sent to the target node. The difference here is that from the normal full sync replications, that we don't send the entire key set to the target node. We only pick the that are in the slot to be migrated, and then sending them to the target node. Additionally, we don't send the key as a whole. Instead, we're using this AOF format as opposed to the RDB format. The AOF format would allow us to send individual fields or members of a collection to the target. This way, we mitigate the large key issues. We're really, we will be using a lot smaller memory footprint on the target node, making the migration a lot smoother. So this slide shows that the migration of the very first key, and obviously when we talk about atomic slot migration, we're not talking about like the migration itself is atomic. Sending any data requires time. So the keys are still being moved one by one to the target node. The difference here between the new atomic slot migration and the legacy slot migration is that the keys that are migrated are not deleted from the source. The source still has the source of the truth for all the keys, giving a full view to the client applications. Now, obviously, during the slot migration, changes can be made to the source node as well. What's shown here is an addition of a new key C here, but things like deletes and also updates can happen to the source node, and A and B can either be updated or deleted. All these changes are saved in the same replication backlog, as if that for that to be sent to the replicas and then the target node at a later time. So this accumulation of data will continue until all the keys in the snapshot will be migrated to the target node. At some point, the target node will receive the full snapshot, and this is the time that the child process will exit, and then we're entering the normal replication stage, which is not much different than the existing replication, incremental replication. And then the source node will start processing the changes in the replication backlog and then start sending those updates to the target node. Eventually, you can see here, the new key also showed up on the target side. Now we have identical keys on both sides and then with their own values, most up-to-date values. This brings us to the last step, which is to perform this handover, and then we change the ownership from the source to the target. This is done in an atomic way so that clients will be redirected to the target without ever seeing any partial results in the cluster. This basically concludes that our atomic slot migration workflow, and hopefully that this is useful for you guys. Thanks. And now I'm going to hand it over to Ren to talk about the HFE feature.
Yes. So hi everyone, I'm Ran. I help maintain Valkey. I also work at AWS. So I'm going to talk about hash field expiration, which is a new feature that was really one of the top requested features that we had for a long time. But before I go and dive into the details of the implementation and the consideration that we took, I want to first take a look at what basically hashes are. So we're talking about Valkey. Valkey is a key value database, and usually when you think of that, you think about like a key which is like mapping you into some kind of string. But Valkey actually supports a lot of different kinds of values. Like for example, you can map a key to a simple string, you can map a key to a set, you can map it into a hash. Okay, and when a key is mapped into a hash, is basically saying that this is what we call the hash object. Okay, now the hash itself is also some kind of a sub-dictionary, a sub-map that we keep inside, and it helps like group together a lot of key value pairs. Now, Valkey also supports a feature which is placing an expiration time or a time to live on a specific key, okay? When you have a string key, a set key, or a hash key, or whatever, we have all sorts of different type of keys. You can also set like a time to live on that one in order for it to be like removed from the database once the time has expired, once it was expired. And this part is being driven by two types of processes. The first one is what we call lazy expiration. Whenever you touch this specific key, like either you're trying to read it, or you are trying to override it or change it, or something like that, that key would basically be expired. It will be deleted, and the memory will be eventually reclaimed to the operating system. Now, there is another way which is called active expiration, which is being driven by a background process, okay? Because let's face it, we're not always touching all of the keys. Maybe we will never reach and touch that key ever again, so we still need a way to delete it eventually after the time expires. So we have some kind of background scanner job that scans over the keys that have assigned expiration time, and it evicts them. So this is what we call active expiration. So what is it like a hash field time to live, and what is it good for? So as I said, we have the way, Valkey already offered a way to place an expiration time on high-level keys, but when you get into the fields of a specific hash, there was no way to set an expiration time on it. And why do we even need it? So this is something that is widely requested in order to perform different hot call data management during session store workloads, feature flags. Sometimes you have different features that you want to place TTL and then like expire the enablement of this feature, etc. When we started to work on that, we mapped what are the challenges that we do have here. So the first challenge was to introduce some kind of mechanism that we can track the keys that have expiration time of a specific hash. Now, hashes can be small, like 10 elements, 100 elements. They can reach even like tens of millions of elements in some cases, okay? So this was one challenge. Another challenge here was the complexity of the command. So hash object is something that offers you to access the specific fields and their matching values, okay? But it needs to operate at a constant complexity, like O of 1. And like having introduced a secondary index in order to track these items also makes us more careful about not causing any implication on the complexity of the commands, and we want to keep the hash as efficient as it was. And other considerations are, of course, always the memory and performance. Valkey is an in-memory database. It should perform like the very high throughput, and of course, we should always place a cap on the amount of memory overhead that we're introducing while we're introducing a secondary index. So when scanning through the solution, the first naive solution was, okay, we have like a hash table, basically, because the hash object is being implemented internally by a hash table. And so we can introduce like a secondary hash table that only maps to the specific fields and values that are assigned with a specific expiration time. And that's nice, and that's fine, and that's very efficient. The only problem with that is that we don't have a way to scan them like by their expiration time. Because, so basically, if we want to search, if you remember the background process, if we want to search items that have been expired, we will also scan items that have not been expired, and we waste a lot of CPU cycles doing so. So another naive solution is to use some kind of sorted data structure, for example, a radix tree, in order to store the elements by their specific timeout. And this is something that is basically used already inside Valkey in some cases. The only problem is that when the entropy, the data entropy is very large and very high, so this can consume a lot of memory. Like, for example, we measured about more than 54 bytes per each element, okay, that is being tracked in this data structure. And this is something that is of course, something that we would like to avoid. So another solution is to use maybe a slightly better data structure that is more efficient in terms of memory, like let's say, for example, skip list, that is also a data structure that is widely used inside Valkey. The only problem with skip list is if we take, for example, a very big hash and we have a lot of elements that has assigned expiration time in that hash, we get a logarithmic access time. And as we said before, most of the hash operations operate in constant complexity, and we don't want to introduce a logarithmic complexity to hash operations. So what we end up doing is using something that is used in some cases in the industry. For example, Kafka makes use of this design pattern, which is called coarse buckets. Okay, coarse buckets is basically saying, okay, I have a lot of elements that share about the same expiration time, so let me place them into the same bucket. And that way I get some kind of semi-sorted data structure. And I can iterate over this data structure bucket by bucket, stopping when I get to a bucket that has expiration time which is higher than the current time. And I can just like assume that all of the items inside this bucket has already been expired, and I can, of course, delete them. And so this is like very high level. Of course, the bucket system and the algorithm itself is much more complex, and we have different ways to split buckets and to encode them in different ways that are more efficient and memory in terms of memory and performance and CPU. But this provides us both constant lookups and modifications. And if we look at the numbers, so in terms of memory, we look at different dimensions here. I wanted to show you that it matters like how your workload is being defined, because it has some kind of impact on the memory utilization. Like in this diagram, for example, I'm showing the overhead of keeping the memory per each item. It's different if you have like different expiration time set on each element, or for example, you have the same expiration time on all of the elements, okay? So it matters. It matters because of the internal metadata of the data structure being used. So we do know that it can be about 16 bytes to 26 or 27 bytes, depending on your workload and how it's structured. In terms of benchmarking, so if you can see, like, if you're not using this feature, like, for example, you have hashes without items being set with time to live, and you have, like, hashes with items, so the performance is basically the same. So we did that, okay? That one is, we are still keeping the constant time. Regarding, yeah, thank you. Regarding the new commands for the hash field expiration, so there are new commands that are supporting, manipulating, setting the data, the hash fields with time to live. And as you can see, they reach about the same throughput as the regular hash command, so it's constant time. And they're also operating very much the same, whether or not you're using a very large hash, for example, a single hash that holds like 1 million items with expiration time, or a lot of small hashes that are using internally have, like, I don't know, many fields with time to live set. Another thing that I think that this one is interesting, and it's also meant in order for you to understand that how you build your data inside inside Valkey matters. For example, what we did here is taking 10 million fields, hash fields, with expiration time which is already has been expired. Like, you have 10 million fields that the system needs to delete, okay? And then we measured how much time it takes the system to really delete all these elements, okay? And like, if all of these elements were placed into a single hash item, like you have a single key in the system holding 10 million items that have been expired, it can take up to 26 seconds in order to delete them. However, if you take the same 10 million items and you place them into 100K hashes, different hash items, different hash objects, it will take like about 6 minutes. 6 seconds, sorry, not minutes. Okay, 6 seconds. And you're asking, why is this? Okay, it's because the deletion, like when we are actually like finding an element, when we find an element which has been expired, we need to remove it from the hash object. When the hash object is very big, we're less hitting the L1 cache layer, and we're hitting the low-level cache layers, which of course takes more time. This, we're about to finish. This one shows how the background expiration job works in evicting items. So in this case, the memory is being governed by the injection throughput, which is basically, in this case, is the requests per second that are setting more and more data with expiration time to hash items. Of course, if you multiply it by the average time to live and the average memory that it takes for each item, then you reach a kind of a formula of how much memory the system should hold. And as you can see here, the background expiration job actually does the work, and it maintains a bounded level of memory overhead. Just a small peek about the next step. So we are planning on introducing a lot of memory efficiency improvements to the hash field expiration, as you saw before, like the memory overhead. We are planning a lot of improved performance to improve these using different techniques like memory prefetching and SIMD instructions. And we are planning also to extend the functionality if you guys, of course, vote and +1 on issues suggesting that. About suggesting the same functionality for set objects, for example, and other cool stuff that we can do. So we talked about 3 major features that were introduced in Valkey 9, but this is just like some of the major features. We also did a lot of different work, which was very exciting and and had high impact on both the performance and the efficiency of the system. For example, zero copy requested, which without going into the details, introduced like 20% higher throughput. We have support for multipath TCP, using the multiple TCP streams in order to pass the data. Memory prefetching for pipelining commands. Where is Victor? Thank you, Victor, for that one. We introduced up to 40% higher throughput when you're using pipeline requests. Stability improvements for the clusters. We are also we constantly trying to use the modernized CPUs. For example, SIMD instructions helped introduce by 200%. Mehdi, thank you. The bit count and hyperlog commands. New filtering objects for the client list, which is great for observability and understanding which clients are currently connected and what they're doing. We also added some ways to perform a kind of set and get operations, and del if equal command was also added in order to perform some kind of smart deletion. Also, geospatial, we have a lot of geospatial support in different commands, so we also extended these ones. And it's keep on going. The list is very long. I won't go over all of it. I would just like to thank all of the people that are constantly contributing to the project. You have the full list here. Let's go over it one by one. Just kidding, okay? But there are great people. Some of them are in the room, some of them are not. But it's a great community, and we keep on growing, and you are all invited to join. Thank you.
So for this, we did specifically have time for questions. If you have any technical questions, not technical questions, we have Kyle with a microphone. So if you have a question, raise your hand, and Kyle will give you a microphone, so the recorded audio will pick it up.
So regarding atomic slot migration, which is a very exciting thing. The one thing that we noticed is it was just the speed that with the old slot migration, it was very slow to migrate over a lot of data. So that's basically made it impossible to scale very quickly. So how much did you measure how fast the new one is compared to the old one? That's my question.
I think there's even an issue that says measure how much faster it is.
Okay, because to us it seems like the number one reason to do this, because we didn't have issues with the large keys, for example, and the other things like that.
Yeah, it should be a lot faster because we are now. So the previous process.
So I asked just to ask if you have some numbers about that.
No, we don't.
Yeah.
I was just going to explain for the people in the room, like the existing legacy one has a separate client that you have to basically pull the data in and then push it over. So we basically remove all that hop, remove all that processing. Yeah, it's a lot faster.
A question about your very first slide. Why are we having a BSD license and not a GPL license?
What a great question. So this gets back to kind of in like I don't know why I'm going. There's too many slides. We're just going to leave it here. So when the fork initially happened, so Valkey, Redis, where we forked from, was historically a BSD license. And so we evaluated a lot of stuff. The one we were there was two licenses we considered, which were LGPL and MPL, so Lesser GNU public license and Mozilla public license. And the initial set of control, one of the things we were concerned about was initial adoption, and those licenses are just enough of a hurdle for people to be like, oh, I have to go talk to lawyers. And so a lot of our initial contributors and people working on the projects did really want to keep the original license, because then it's a drop-in replacement, right? Since we were kind of reacting to moving away to like a proprietary license. So we kind of wanted to just keep the license the same. The second thing is a bit of a personal philosophy of mine and some others, which is that I think as long as you have a strong community around a project, you don't need a license to sort of keep the code open. We like to encourage contributions from like corporations and big organizations who might be a little bit hesitant to immediately contribute to something when they like have to give their code back. So we're okay with them kind of keeping their code internal and then encouraging them to keep it open. So we really do want kind of a big open source project, but like that's my philosophy. Other people might have slightly different ones, but and again, I'm just one of 6 people on the TSC, the Technical Steering Committee of Valkey. I can't unilaterally decide what the license is, but this was sort of the consensus we had as a group.
Hey, I have a question on this slide.
Perfect.
So my first question is about client protocol. So with this change, does that change, for example, do we still need ask response, or how does it change the client behavior?
Yeah, another great question here. The client behavior actually is simplified. You no longer will see ask.
But we still see moved, for example, right?
Yeah, you will see moved when the slot ownership change hands.
Would there be an announcement of the protocol change because all the clients needs to update on this as well? No?
Yeah, because... Okay. It's actually a simplification of the existing protocol.
They will continue work.
Yeah, you will continue work, and then you actually see less disruption from the client side.
That's great. Thank you. I have a second question on this slide. Sorry. So I wonder what would happen if the source crash in the middle of this process.
It will get canceled in that case, and then everything will be back to the normal state. It's as if nothing happened.
As if nothing happened,
Yeah.
but would there be a let me see.
So up until this slide, so like this is up until this slide, the source owns all the data. So all the requests are going to the source. And then after the handoff, all requests go to the target. So basically any failures before this point on the source or the target, everything just gets aborted. It's on both. So that's why we pre-stage all the data on the source and the target.
So you're going to clean up the target?
Yes.
Okay, thanks.
Hi, thanks for the talks. This is a bit of a layman question for slots, and probably a Googleable one, but while I have you here, the modulo 16384, was it? The 14-bit number?
Yeah, it's to the 14th.
What's with that? Is that the max number of nodes that you can have in a...
No, it was originally just picked because it was a good number. You'd be surprised how often like people pick 2 to the 14th as like it's big enough that you get pretty good distribution. It also is picked pretty well to kind of hit the upper limit of where clustering makes sense. We also abuse, I don't want to say abuse, we use the fact that in 64-bit memory spaces, we have about 16 bits up at the top that we can use, of which 2 to the 14th is smaller. So we can use that fact for in some internal, so when you're like scanning through a cluster, we use those 14 bits to basically determine like which slots we're in. And then you basically get 32 bits for the number of keys you can have, and then 14 bits for the slot you're in. So there's some usefulness. And 2 to the 48th is like the upper bound for how many keys we could have, because then we'll literally not have, Linux won't be able to allocate that much memory, or any major operating system. So it's kind of just a pragmatic choice. It's not structurally required. We could go to 2 to the 16th. But yeah, and also right now we support about 1,000, 2,000 nodes. At that point, you have about 8 slots per node, and that's kind of like a good point before you start seeing too much distribution in the keys between nodes. So yeah. So Victor said it is the current upper limit on the nodes, which is a true statement.
But don't do that. No, don't do that. Other questions?
We would like someone to try, though. That would be fun.
Martin.
I would like someone to try. Yeah.
Sorry, back to the slot migration again. The replication backlog, is that still the original replication backlog as in per shard that you're using? You haven't moved it to a slot level as well?
Yes, I think, yeah.
Isn't it slot level? It's slot level.
It's not slot level, it's the original one. I think the question...
Ping, use the mic.
Okay. I think Martin's question is that whether we're using a separate replication backlog. I don't think we're using that today. Obviously, I need to look at the code one more time. But yeah, so in the future that we could optimize that. So right now it's mingled with other payload as well. Yeah.
Other questions?
I will say, if you like this series of talks that we did this morning, you should be in track 1. If you're like, well, these people are too technical, track 2.
Track 2.
Track 2.
Yeah. Other questions? Any questions? Yeah? Okay. Joseph.
Yes, Vadim?
Yeah, hey. Question about slot migration. The replication backlog. So, do we have any mechanism to basically back off the pressure? Because when we're in the stage when we have the replication backlog, if the clients put too much pressure on this specific slot, we might stuck in this state for a long time.
Yes.
Or it's like something that clients should do, or we have some mechanism to like block or back off or something.
So today there's no mechanism, but I see you're from AWS, and I saw AWS has some pretty advanced technology in this space, so we would love a contribution.
Other questions?
Just to comment to this previous one. Before their handoff, we pause the writes to the source shard, to the source node, so we don't have any writes while we do the handoff.
Yeah,
right?
But that's just for the handoff phase. Before the handoff phase, we do need to drain the queue, which...
Okay.
And basically, normally when like you have incoming traffic, it's what we call metastable. So either you're going to drain the queue, or you're never going to drain the queue. And at that point, it will disconnect and abort. So one of those two will probably happen. Unless you like tune your throughput to the rate of the migration.